Okay, I will record now. It's recording, so I will share again my slides. All right. Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning to everyone. Ahlan wa sahlan, and welcome to our seminar series from the Photonics and Radiation Research Group, from the Electrical and Computer Engineering Department, Kulliyyah of Engineering, International Islamic University Malaysia. First of all, we will have some introduction to our research group, and here's our website and Facebook if you like to follow or join any of our activities. Okay. This is the some introduction of our members in our research group. We have 11 members altogether. Me, myself, Dr. Nur Fazin Hasbullah, and Dr. Norzaini binti Saidin. She's the research group coordinator. And then we have Dr. Suriza Ahmad Zabidi from the same department, Electrical and Computer Engineering Department. Dr. Shahnan Zainal Abidin, also from the same department. Dr. Bilal Ahmad Hamidah, also from the same department. Dr. Nurul Alfa and Dr. Aliza Aini, also from Electrical and Computer Engineering Department. Two more from the same department is Prof. Dr. Hadi Habaibi. He's our associate member, and Dr. Shahrin Abu Hanifah, also our associate member. And from another department, from the science department, is Dr. Nurhanis Aida, and Dr. Nur Idayu Ayub, also from another department, which is Material Engineering Department. Okay, so I'm admitting people while, so it's a bit slow. Okay, next, just to share our vision and mission of our research group. Our vision is to be recognized as an excellent higher education photonics and radiation engineering research center. And our mission is to produce high quality research in the areas of photonics, radiation, and engineering. The research area, our research area at the moment consists of these six elements, including visible light communication and free space optics, nonlinear and ultrafast optics, optical fiber technology, fiber optic sensor, and nano photonics materials, semiconductors, physics and devices, and radiation damage study, and optical and electrical characterization of semiconductor devices. We have a few collaborations at the moment. Actually, we have USM over here. We haven't updated the slide, I think. We should add USM with Dr. Zaini. So we have from Nuclear Malaysia to University of Sheffield, University Malaya, and Angkasa, Malaysia Space Agency. Here are some of our research group activities. We have a talk like seminar like this, and we also have sharing grants from other researchers. This is our friend from the Kulliyyah of Science, IIUM. So we also have demonstration in the labs generally. So today, brothers and sisters, ladies and gentlemen, we are honored today to have a speaker from USM, Dr. Zainal. And the topic of today's webinar is on reducing dislocation density in aluminum nitride or on sapphire template through novel MOCVD epitaxy for improving efficiency of UVC LED. So it sounded very interesting, so we will hear from her, inshallah. I will introduce now. I will introduce the speaker, Dr. Norzaini, a bit. Dr. Norzaini Zainal is currently an associate professor at University of Science Malaysia. At her early career, she spent almost 2 years working on cubic gallium nitride material, which was an extended project from her PhD work at University of Nottingham, UK. Later, she initiated a new research team in nitride semiconductors, focusing on controlling properties of nitride thin films through base structuring in nanoscale and base crystal association. Base crystal orientation, together with manipulation of processing physically and thermally. Her teams keeps expanding each year, and currently she has 5 PhD and 1 MSc students. Funding from Malaysia government through National Epitaxy Program, gallium nitride on gallium nitride, has given an opportunity for her team to expand their work into designing and developing light-emitting diodes, LEDs, using epitaxial technology based metal organics chemical vapor deposition, MOCVD. In particular, her team is focusing on increasing efficiency for LEDs operating in UVC spectrum as well as in longer spectrum from green to red. Through the program, her team has collaborated extensively with University of California, Santa Barbara, USA, University Malaya, and Osram Opto Semiconductors. Apart from that, she has initiated connection with few groups abroad, King Abdullah University of Science and Technology, KAUST, University of Sheffield, United Kingdom, Graz University of Technology, Austria, and University, this one I don't know how to pronounce it, Coty or Cote, maybe Dr. Zainal can mention later, from France. So basically that's the introduction to our speaker today. And again, for those who just arrived, you're welcome to this webinar. And now I would like to invite, without further ado, I would like to invite the speaker for today, Dr. Norzaini. So you can share your screen.
Okay, I need to share my screen. Okay. Oh. Can you hear me and can you see my screen?
Yes, yes, we can.
Yes, all right. Okay, so right, I can start now, I guess. All right, okay. Assalamualaikum and good morning, everyone. My name is Norzaini Zainal, and I'm from Institute of Nano Optoelektronik Research and Technology, IIUM, University Science Malaysia. And before I start my presentation, I would like to thank Dr. Nurul Fazlin for organizing this talk and her team, okay, as well as thanks to the rest of you for being here virtually. Right, so the title of my talk is Reducing Dislocation Density in Aluminum Nitride Sapphire Template through MOCVD epitaxy for UVC LED development. And this is one of my current research project at USM. Okay, so a little bit introduction about myself. I work at USM, okay, at School of Physics from 2010, right after I finished my PhD, until early of 2015. And then since then, I work at USM, all right, until now. And I obtained my PhD degree from the University of Nottingham in 2010. Before that, I studied in USM for my bachelor and master degree. So currently, I'm supervising 6 PhD, 6 students, okay, 5 PhD and 1 master. And I have graduated 6 students, well, 1 PhD and 5 master MSc student. And from there, from the statistic, you can guess that all my master, 4 of my master student continue their PhD, right? And so far, I've worked with various scientists around the world, okay, University California of Santa Barbara, the University of Sheffield, and then KAUST in Saudi Arabia, TU Graz, and University Chote de Arthur in France. All right, so this is the outline of my talk. I will start with introduction to USM and IIUM because not many people know about IIUM and also USM. And then subsequently with the introduction of nitride research, particularly the research activity we have done at USM. And also following that, I will describe my research activities on aluminum nitride sapphire template for UVC LED development. So now moving on. So to those who are not familiar USM, the main campus of USM is located in Penyelidikan Island. All right, and then we we are connected to the mainland through these two bridges. The closest one to USM is the first bridge, okay? Right, and then USM was established in 1969 as the second university in Malaysia after University Malaya. And formerly, it was a site for British military camp. So if you come to USM, you can find that there are few British colonial buildings still be around in the campus. And so far, USM has offered various courses and become a home for international students from various countries. So if you come to USM, you may find there are many beautiful spots, okay, for relaxing, hanging out with your friends, okay, gossiping, and also photo shoot for your Instagram, for example. Right, so USM is practicing a concept called the University in Garden in the effort to signify the role and the function of USM in a fresh natural environment. So I'm sure that many of you know that USM has 3 campuses, one in Penang Island, okay, our main campus. Then we have engineering campus in Nibong Tebal, Penang. Nibong Tebal is just a border between Penang and Perak. And then we have Hubs campus in Kubang, Kelantan. But in addition to that, USM has another other 3 campuses. Okay, not many people know about this. All right, so first we have signed at USM campus in Penang. It's just opposite to the Equatorial Hotel at Bukit Jambul. And then we have AMDI, IPPT, okay, at Kepala Batas Penang. And also we have KLE USM campus, which is serve for offshore program for medical science study. All right. So introduction about INO, Institute of Nano Optoelektronik Research and Technology. Okay, basically INO is not located in the main campus, okay? We actually located at, signed at USM campus. However, INO and USM, the main campus, not far, okay, from School of Physics, which is located in main campus. It just takes you about 3 minutes to reach sign as USM. So distance is not a big deal for us because quite many of our students still staying at the hostel in the main campus. All right, so just a little bit introduction about INO. INO was established in January 2015, and the first director is Professor Kamarul Aziz Ibrahim. I'm sure that many of you know him. And then the current director is Professor Zainal Hassan. And for some of you who don't know about INO actually is upgraded version of Nano Optoelektronik Research Lab at School of Physics. Okay, this lab is the first lab in Malaysia which equipped with state-of-the-art facilities and equipment for conducting semiconductor research. And for your information, no lab still running until now. And it start with I know start with 4 academic staff, and then we keep expanding. All right, and now we have more than 20 staff that I know. And if you would like to find out more about us, please visit our website and Facebook page as shown on the screen. All right, moving on to the nitride research at INO. So some of you may ask, okay, why we go for nitride? Okay, for your information, nitride has been identified as one of the most important material for 21st century. However, if you ask some nitride expert, they're quite biased. They say that nitride is the only more important material for 21st century. So far, nitride lead to huge advancement in many applications, for example, lighting, disinfection, high power and high frequency operation. And it's not exaggerate to say that nitride leads to substantial benefit to our life. Right, for those who are not familiar with nitride, okay, this material system can be formed by combining element from group 3, aluminium, gallium, and indium, with nitrogen from group 5. All right, so by adjusting the aluminium, gallium, and indium, okay, we can have binary, ternary, and quaternary compound of nitride. And as compared to other material, okay, nitride has wider and direct band gap, and which is allow the device based on them to operate at higher frequency, power, and temperature. And commonly, nitride exists in hexagonal structure. And for LED and laser diode, okay, the emission wavelength of the device can be tuned from far UV to infrared by adjusting the composition of aluminium or indium in gallium nitride material. So this is one of the unique properties of nitride. Despite of that, not many people in Malaysia working in this material. Okay, do you know why? Because it's it's an expensive technology. For your information, in order to have to obtain high quality quality nitride, we only can have that kind of material through epitaxy, which is the process which involve atom by atom mechanism. This means that the nitride requires such a delicate and complicated process, right? So on that note, okay, Malaysia government through Economic Planning Unit has set up a national epitaxy program called GAN on GAN, and this program focus on establish nitride technology through blue LED development. Okay, through so this program received funding for more than 70 million just from the government. It's not okay, not including contribution from the industry and in-kind contribution from the university who involved. Okay, this program has started in 2015 and will end by next year. So GaN on GaN, what is that? Okay, GaN on GaN LED means that we grow nitride LED using gallium nitride substrate. And with the use of the substrate, the brightness and the efficiency of the LED can be significantly improved. And furthermore, not many people are working on this area yet. So it gives opportunity for you, for Malaysia researcher to lead in this area. All right. So in this program, okay, the final performance of the program is to demonstrate 150 lumens per watt blue LED on gallium nitride substrate, which will be used for developing white LED with the use of phosphor technology. Right. Okay. So this program involves extensive effort from the government, agency, academia, and industry in Malaysia. And EPU has given mandate to CRES, okay, to manage this program. And UCSB, University of California, Santa Barbara, has been chosen as our technology provider to transfer the technology of making LEDs, okay, to our local researcher. And this technology was invented by Professor Shuji Nakamura, who a professor at UCSB, and won the winner of the Nobel Prize in Physics 2014. So under this program, USM and UM are responsible to absorb the technology in terms of epitaxy and fabrication of LED, while UNIMED and USM through School of Mechanical work on packaging, while Monash University work on computational study. All right. So of course, I mean the technology, if you can see here, is technology from academia to academia. Okay, USSB to university in Malaysia, and in parallel, our industrial partner, Austrian, will help us to fabricate our grown LED using industrial standard. Okay, while Inari, Pancake, and Tralmas will help us to pack our LED also using industrial standard. So how this program benefit to USM? And through this program, USM receive a world-class equipment and facilities to support the nitride research activities. And the major procurement is metal organic chemical vapor deposition, MOCVD, which allow us not only to grow blue LED, but also green and UV LED. All right. So means that, okay, under this program, okay, we have a team at USL who work on blue LED to fulfill the target of the program. And at the same time, my team, okay, and my student work on green and UV LED as the expansion project from the program. So so the idea is to maximize the capacity that we have. Okay? So, and on top of that, we receive a complete facilities to fabricate our LEDs, okay, mask less lithography, spin coater, RIE, E-beam evaporator for metal and oxide, and also rapid thermal processing. But some of the equipment still under commissioning, and the delay is due to the COVID-19 situation. Then meanwhile, these characterization facilities already been around at USM, I know, and physics, right? And then this procurement is the procurement of this equipment is not funded under the program, so it's already been there before the program. All right. Now we move to introduction to my teams. Okay. Right. So basically, my team quite small, but it consists of 5 PhD student and 1 master student, and 4 of them working on green LED, while these 2 guys use Nizam and Esmet are working on UV LED projects. Okay, so now I'm going to present our finding from the UVC LED project. So before I present to you on what we have done and what we have found from the project, allow me to explain to you in brief why UVC LED become important nowadays, and hence motivating us to work seriously in this field. Okay, by looking at the curve, you know that the number of new cases due to COVID-19 keep increasing day by day, and there are 3 core strategies to face this pandemic, and that among them, prevention is the key to flatten the curve, right? So while COVID-19 is looming over us, okay, UVC LED has proved to kill the coronavirus in seconds, okay? So therefore now, UVC LED receive huge demand in the effort to prevent the spread of COVID-19. Nevertheless, the current UVC LED are only few percent efficient, right? And then therefore they are not ideal for disinfecting the viruses on large scale. So in order to make the LED useful in the context of COVID-19, therefore the efficiency of the UVC should be improved. Then from the fundamental standpoint, okay, there are 2 major problems to improve the efficiency of UVC. One is the difficulty to obtain high p-type conductivity inside the LED, and then the second one is is due to the difficulty to obtain a low dislocation density in the aluminum nitride layer here, where this layer serves as the base layer for growing the UVC LED. Right, at present, we focus on reducing the dislocation density inside this layer. Why is it important to reduce this dislocation? It's because, okay, the dislocation in the layer tend to propagate into the overgrown LED. All right. So once the dislocation reach the active region of the LED, it will be a nightmare. Okay, there will be less light will be produced, hence lead to low efficiency. So we tackle this problem by focusing on perfecting the gross condition of the aluminum through nitridation and inclusion, and also introducing the TMAL pre-flow. Okay, right. So in the first part of the project, the aluminum nitride layer was grown at the temperature above 1200 degrees C. All right, so because most of the good aluminum nitride growth can only be obtained at high temperature. Right, so in this part, okay, we study the influence of nitridation time okay, on reducing the dislocation inside the aluminum nitride layer. All right, so we can see that from the graph, okay, the optimum nitridation time is at 20 minutes, okay, of nitridation. right? With the lowest dislocation density in this series is nearly 10 to the power 9 centimeters squared. So now how nitridation can reduce the dislocation when it was applied up to 20 minutes. Okay, as reported by Wang groups, okay, here, the proposed model, right, reported in the report, okay, the nitridation help to strengthen the atomic arrangement of the overgrown aluminum nitride layer, okay, and hence this lead to the reduction of the dislocation. However, if the nitridation time is longer than 20 minutes, okay, it tends to promote mixed polarity of aluminum and nitrogen growth. This is what we call the inversion domain, okay? And once we have this effect, it starts to generate the dislocation, right? So now, okay, the dislocation density can be further reduced by introducing the nucleation time at 60 seconds. Okay, now we focus on this part, right? And then we see that the lowest dislocation density can be below e to power 9 centimeters squared. All right, and then then the result is quite comparable, okay, quite near to Rican groups, okay, who live in this area. Nevertheless, okay, since, okay, you can see that we grow, okay, in this series we grow aluminum nitride layer above 1,200 degrees C. However, we can for the next experiment, we cannot apply this temperature, okay, because we have to concern about the lifestyle of the heater. You know, for your information, because if we increase the applied high temperature, the lifestyle of the heater will be shortened quickly. And for your information, the cost to replace the heater, okay, in MOCVD, is more than 100,000 ringgit Malaysian. So it's very expensive. However, what we have done, what we have found here, will be used as the baseline to grow aluminum nitride at low temperature, a little bit lower, okay, below 1,200 degrees C. Right. So in this part, okay, so we keep continue, but in this part, we have to reduce the gross temperature of the aluminum nitride. So so when we lower the temperature, the gross temperature means that we have to compromise with the material quality. Is okay. So the dislocation density will be expected to be higher, a bit higher than the one grown at higher temperature. So in order to tackle this problem, okay, we introduce TMAL P4, stand for trimethyl aluminum. It's a metal organic, which is the source for aluminum. Okay, so by introduce this pre-flow, okay, we can form nano island here, and then this nano island actually help to bend the dislocation, and the dislocation will terminate when they meet each other in the opposite direction, okay, as compared to the one without the TMA free flow. Okay, this is the dislocation. There's no way dislocation density can be reduced. All right, and then we believe that such effect, okay, will be significant when the nano island is reasonably bigger, okay, hence which in other words, the TMA pre-flow need to be optimized. So now what's the result we have so far? All right, so we try to, so from the series of TMA free flow time, okay, the dislocation density can be lower at 1.3 10 to power centimeter squared, a little bit higher than those that than the best result we obtained for high temperature aluminum nitride growth. And then as you can see from the graph, okay, the dislocation density reduced, okay, up to 30 second TMA free flow, and the dispersion increase again when the TMA free flow is longer than 30 seconds. All right, so we believe that this behavior is associated to the size of the island. Okay, from the AFM measurement, we can see the roughness, okay, slightly higher, okay, when we increase the temp, the pre-flow time up to 30 seconds. All right, then this it shows that the nano islands start to become bigger a bit, okay? And to be honest, it's too hard to determine exactly the size of the nano island from the AFM study. And for your information, the surface looks smoother for the TMA pre-flow beyond 30 seconds. This means that there's no island formed and the dislocation, inclination, and termination is more unlikely to happen. Right, and then after COVID-19, okay, situation become better, we plan to fine-tune the concentration of the TMAL flow in the effort to further reduce the dispersion inside the aluminum nitride layer. And the potential of our grown aluminum nitride layer was assessed just before the first MCO was enforced. Okay, so we quite lucky, just at the right time. Then from the IV curve, you can see we can observe the diode characteristic showing that we successfully demonstrate a working UVC LED. All right. However, if you can see from the graph, okay, the forward voltage a little bit slightly longer than what we expect, and also the current quite small, and this is due to the poor p-type conductivity of the LED. So of course definitely we need in our next work we need to rectify, improve the p-type conductivity. And the UVC LED emit at the wavelength at 282 nanometer based on what we observe from the CL measurement. Right, so this particular wavelength is perfect enough, okay, to disinfect the virus, okay. So last but not least, okay, our projection for UVC LED is given as follow. Okay, at the moment, there are more improvement we need to do, okay, in terms of improving the UVC LED epitaxy, for example, okay, further reducing the dislocation inside the aluminum nitride layer, as well as to improve the p-type conductivity of the layer. And then once we run up once our fabrication and processing facilities up again, so we will try to work on this part, okay, using novel approach. All right, then but this one is far ahead, okay, where maybe, okay, once we can improve the efficiency of UVC LED, so this might trigger more advancement in this fashion technology, maybe for example incorporating the AI element or robotic element inside the technology of this fashion. So with that, okay, that's all from me. Thank you.
Okay, thank you very much. Let me, how do I change this? Thank you very much, Dr. Zaini, for the interesting presentation. And now I would like, I forgot to mention in the beginning that our, what do you call it, our seminar today is also in collaboration with IEEE Photonic Society. So thank you to the IEEE for Photonic Society for collaborating with us. Now, I would like to open the floor or the screen to anybody who would like to ask question. You can, I don't know how to, can we, I don't know, can we stop sharing first? All right, great. So, and then anybody can ask question in directly, or you can write your question in the chat. Up to you. Come on, the chat. So anybody? So we have roughly, just now we have around 46 now, maximum 46 just now members. So maybe I will start the ball rolling with the first question. I think maybe some of our participants today are students, so it will be great if you can explain the basics. For me, even I tried to Google UVC. Why have a C there? Why is it called UVC LED? Why is it not UV LED alone? And also maybe you can also talk about what is dislocation, the basic term. Can you explain that?
All right, so okay, UVC LED, okay, in general is can be split into UVA, UVB, UVC. So UVA, okay, I'm sorry, it's not in my mind, but is a wavelength between, sorry, I cannot remember this one, but it's something like up to 380, something like that, and then from 380 to 310 is in UVB, and UVC is from 300 and 310 or 300, sorry, 300 towards 200 nanometer. All right, so that's why I said only nitride can develop, so far only nitride can develop UVC LED, because okay, when we go into the shorter wavelength,
I will mute. Ask to mute.
okay, as we go to shorter wavelengths, okay, means that the energy band gap of the active region of the LED need to be higher. So in order to
Okay,
do
I'm
that,
trying to find where's the. For those who are not speaking, can you please mute your mic? Because maybe Dr. Ina can also help me. Okay. All
okay,
right. Please
so
continue.
Done muting. Okay.
okay, so in order to increase the band gap, this Maria, something like that.
Oh, there's still some sound. Ina, let us try. This is the first time we are doing this.
Okay, all right. So, okay, where are we? Okay, so if we go to shorter wavelength, means that we need to increase the band gap of the active region, okay, of the LED, right? So, in order to increase the band gap, so that's why we put more aluminum into the gallium nitride material, right? But the process is not simple as that, all right? Okay, because aluminium, okay, from the epitaxy point of view, aluminum is hard to incorporate with gallium nitride, okay, as compared to indium. Indium easier for you to incorporate with in gallium nitride, but you need to be careful, okay? It's easier to incorporate, at the same time it's easier to decompose or run away from the gallium nitride if you what you call it, apply at low temperature, higher temperature. But for aluminum nitride, for aluminium, it's kind of, I will say, a stubborn atom which is refused to incorporate with gallium nitride. Okay, so that's why by force you need to, in order to make it incorporate into the gallium nitride material, that's why we need to apply high temperature.
I see.
Right. So okay, then you have second question. I cannot recall.
The second
Oh,
question.
dislocation.
Yes.
Okay, dislocation is okay. If you can see the emanation that I put just now on this in my presentation. Okay, it's actually quantification for the dislocation for the material degradation. All right,
So
means
it's a
that
type of defects, right?
yeah, it's a type of defects. I would say, but if
Show
you
the
go,
slide again. Maybe you can show from the slide where is the dislocation located, isn't it?
okay, all right, okay.
Okay.
Okay, let me share the screen. Okay, right. Sorry.
That's okay.
Okay, funny.
Boleh tak?
We
Okay,
all
okay.
new to this. Semua baru.
Okay, sorry.
Very interesting.
Okay. Can you see? Oh my God. Okay, right. Okay. So I would say that okay, maybe I need to start how the dislocation is generated. Okay. If any material, not only aluminum nitride with fire, okay, any material which involve, okay, has different lattice mismatch or different properties, okay, once you, okay, for example, aluminum nitride, okay, it has different atomic properties as compared to sapphire. Means that, okay, when we grow aluminum nitride on sapphire, it tends to generate what we call it misfit dislocation here in the interface, okay? Then the misfit dislocation, as we grow the layer, okay, the misfit dislocation will transform into dislocation. Then this dislocation, okay, has two types, screw and edge dislocation. All right. Then, for nitride, okay, edge dislocation, okay, give impact, significant impact to the LED performance as compared to screw, right? So I'm sorry because I don't have, I wish will be there physically so I can write something on those
Yes,
board,
yes.
but
Okay. Tak
all
apa.
right. Okay.
You change it to online. It's supposed
Okay, okay.
to
So means that, okay, then the discussion tend to not stop there. I mean, it tend to propagate into the next layer, right? So that's why the problem will be a nightmare. Okay, will be a big problem if it reach the multi-contour well here, the active region of the LED here, where this dislocation tend to introduce non-reactive recombination reactor, or kind of a trap level that trap the hole from combining with the hole. Okay, so there's no light, right? Okay. I hope that's clear. Some of you.
Okay,
Right.
thank you.
Right.
Thank you, Zaini. Any more question from the floor? The screen.
Dr. Zaini, just now the dislocation is only happen when we incorporate the aluminum nitride. If let's say, I mean, normal UVA and UVB, is that problem happen as well, the dislocation?
It's happened not only aluminum nitride or whatever. It's happened when you grow your LED on non-native substrate. So for example, sapphire, silicon is non-native substrate for the nitride. So that's why we go for GaN on GaN LED, which means we grow nitride LED on gallium nitride substrate. However, for UVC LED, we cannot use gallium nitride substrate. Supposedly we use aluminum nitride.
Because you want to get that UVC, isn't it?
Yeah, because gallium nitride tend to absorb the UVC LED, because lower bandgap material tend to absorb those. Yeah, all right. So, however, aluminum nitride substrate is so expensive. It's so expensive, all right. And also gallium nitride substrate, but with advancement, with fabrication and technology nowadays, okay, we can. Some scientists manage to reduce the price for the gallium nitride substrate, right? So maybe in the next 5 years, okay, gallium nitride substrate maybe cost about similar to sapphire. And for your information, at the moment in industry, we're still using sapphire as the substrate to grow LEDs.
Oh, I see.
Right.
Okay, thank you. There's a question in the chat. Doctor, what is the nano island mentioned before?
Okay, nano island. Okay, it's actually kind of it's a, okay, from epitaxy researcher we call it 3D growth, which means we have a kind of lump or features like nanostructure, but we introduce through TMAL preflow. So the preflow actually introduce so-called promote 3D growth, aluminum nitride in the not a full layer, but in terms of 3D structure. All right.
Okay.
So we not okay. The question is, are we only got aluminum is only, or aluminum nitride island, or aluminum island? So it's hard to tell. But from our observation, mostly it consists of aluminum nitride. Okay, because aluminum itself, even though we only apply aluminum source, okay, tend to incorporate into the aluminum nitride layer underneath, okay, and then form aluminum nitride 3Ds. Okay. But to be honest, I cannot confirm that. Okay, we need to have further investigation. But okay, all right. So we have
There's another question from Sister
question,
Anati Shahira. Salam, Doctor. What is the equipment that we use to see the edge or screw dislocation in a commercial LED?
Oh, not only commercial LED, but any LED. Okay. Okay. Okay, for I would say what do you call it? You know, we have B40, M20, T20, right, in Malaysia. So in research group also we have that kind of brackets. So I would say our group B40. So B40 research group like us, okay, usually use XRD just to estimate. Okay, the edge and screw dislocation. So from the SRD, okay, there's a two type of scan. Okay, you can use 102 scan or 002 scan. Okay, it's omega scan, true omega scan. Okay, right. So for those students, okay, special student, if you want to send your sample for SRD, make sure that you know what you looking at. Okay, so if you concentrate to know edge and dislocation, screw dislocation, we can use SRD. Okay, but it's just estimation because the 002 SID 002 scan quite sensitive to screw dislocation component, while 102 scan sensitive to edge dislocation. But it doesn't mean that it collect all the data with regards to the edge or screw dislocation, just estimation, right, for SID. But if you kind of T20 research group, okay, you can measure the screw and dislocation density through TM, transmission electron microscopy. It shows you a real dislocation profile, okay. However, it's very expensive too. So only T20 research group, okay, can afford that, right? Okay, so however, to be honest, it's not only, I mean, you have the machine, okay, you just send, you measure, then that's it. No, you cannot get this result straight away from TM. So you need an expert, okay, to capture which angle, okay, and then to analyze the result, to process the data and so forth. It's not really straightforward process. But SRD, if you want to publish in paper, SRD quite is perfect enough to show to the to show that you have edge or screw dislocation.
Is the SRD available in INO?
Yes, we have actually, we only receive our new brand SRD broker, okay, at I know. Then for your information at School of Physics, okay, at No Labs now, okay, they also have SRD but panoptical.
But what?
Panoptical model. It's different model.
Oh.
I know we have broker, while No Lab we have panoptical. Okay, then Dr. Shami, those who know Dr. Shami at UM, okay, they have a brand new SRD, but different model. It's called Rigaku.
So what's the difference between the model?
Right, see.
Just the price lah, how the output is roughly the same.
Output roughly the same, okay. But for me, I personally prefer panoptical because it's widely used, okay, across the globe, and the result quite convincing. But that's my personal view, okay. And then the way, because I'm familiar with panoptical, so easier to transfer the data from the machine to the computer for editing or and so whatsoever. But basically, if you try to claim, okay, hey, I already managed to produce low dislocation density aluminum nitride layer, okay, based on SRD, it's better you double confirm with various SRD. It's not only depend on one SRD measurement. Okay, if you want to claim that you will break the world record, okay, we have the highest quality of aluminum nitride layer, okay, this is our result. But if you only depend on one type of measurement SRD, is quite skeptical. So better support with, okay.
So is that means XRD machine, it is a special machine to actually measure this 002 and 001 peak, isn't it? The UVC.
Yeah, but on top of it, because okay, for nitride, okay, normally we use SRD for to measure the screw and edge dislocation for the estimation, and also what you call it RSM, reciprocal surface mapping, to investigate the strain state. inside the LED or the layer, right? But for some people, people normally they just want to, what you call it, to do face analysis, quite enough for them, because just as long as they can see the pit that show the evidence, okay, this particular element exists in our sample. Okay, see. But for LED, okay, when we try to normally we estimate the percentage, or what you call it, the percentage, especially of the aluminum nitride aluminum gallium nitride layer or indium nitride layer. Okay, we use SRD through different scan. We call it omega 2 theta scan. So that one give you estimation the composition exists in your layer, right?
Right. Thank you.
Okay, thank you. There's one more question from in the chat. From Mirza Azhar. How is UVC LED used in everyday life since it can prevent the spread of COVID-19 in a wider scale?
All right. So as I can say just now, okay, at present, okay, the efficiency of UVC LED is very low. Very low. So, but it worked well in small scale environment like portable application, right? In your water bottle. Now you can find market, okay, where you have a water bottle, and then the cap of the bottle is installed with the UVC LED, right? So if you want to clean the water, okay, make sure, okay, there's no pathogen inside it. You can just flush it, and then just for a few seconds, and then that's it. Okay, fine. But because it has, okay, for wider scale, okay, let's say if you want to install the UVC LED, okay, in supermarket, for example. So of course it's a big scale, you know, we need more to install more, what you call it, UVC LED. However, because the efficiency is too low, means that you need more current to operate the LED, but at the same time, the LED just give you, you know, lower brightness. True. So in order to top up the weakness, so you need to install more, put more number of UVC. And then in terms of from the cost point of view, it's not worth it, because, you know, maybe total on a ship, cost on a ship, it just, I mean, not worth it. Okay, if you install low efficiency of UVC LED. But if UVC LED efficiency can be increased, okay, improved in future, so we can install that the UVC LED, okay, in dia building with a small number. Means that we don't have to put more number of UVC LEDs, right? So that's reduce the cost, at the same time reduce the electrical consumption, right? But for the recent technology that I know, they already apply UVC LED in hospital to disinfect the operational theater room, okay, at the hospital, but they're using robot. So the robot keep moving around, things like that. But remember, when you flash out UVC LED, make sure you're not in the room. Okay, let's say you want to disinfect the entire room, make sure you're not being in the room, okay, because it will cause skin cancer, right?
Oh, really? It depends on the power or any power?
Because the wavelength is tough, okay? So for example, actually our sun, okay, consists of UVC, UVA, UVB, UVC. But what reached to us is only UVA and UVB. UVC has been filtered by our ozone. So that's why even though it's short, much longer than UVC, it's not safe, still not safe, because UVA and UVB still cause skin cancer if you expose yourself under the sun. So in other words, I can say that, okay, there's some people asking me, okay, is that UVB and UVA can also contribute to this infection? Yes, I said yes, but it's instead of second, it takes longer time, maybe hours, okay, to disinfect the virus.
Oh, okay.
Right.
Thank you very much. Interesting. Any more question anybody wants to ask from the screen here? No. I just want to ask, when you mentioned your presentation on the p-type conductivity, right? You need to improve. How do you improve the p-type conductivity?
Oh, okay. That's the hardest part actually in the development of UVC LED. So, you know, but we start with dislocation first because it's quite, okay, it's quite easy for, not easy, but we can handle that. But P-type aluminum gallium nitride is not, is totally different, okay, in terms of challenging as compared to introduce P-type conductivity in gallium nitride or indium gallium nitride, because the aluminum gallium nitride has wider band gap. Okay, then the acceptor level, okay, in the aluminum, okay, it's compare, we compare gallium nitride and aluminum gallium nitride, right?
What's the
So
band gap for both? The band
okay,
gap?
gallium nitride is 3.42, while for aluminium gallium nitride, let's say with the percentage 15%, probably about 4 or 5
Okay.
PV. Okay, so because, okay, for gallium nitride it's not an issue because the acceptor level quite close to the conduction, sorry, valence band. But for aluminum gallium nitride, the acceptor level quite far from the acceptor level. Okay,
Valence band.
yeah, the valence band, sorry, the valence band. So means that the hole is not conductive enough.
I see.
Right. So the, okay. So there's many approach to increase, to improve the p-type conductivity, like what you call it, introducing super lattices, and then some of them just
Superlatives to increase I mean the conductivity.
yes,
Superlative.
conductivity to make the acceptor level slightly lower, I mean closer to the valence band.
Okay.
Right, so it's very fun, quite fundamental, this thing. Okay, all right, but to be honest, if you ask expert, you improving p-type conductivity is the hardest part in UVC LED development.
Can I ask why the acceptor level is far from the valence band?
Oh, because the band gap itself, the band gap of the material itself. Okay,
Oh,
one,
because the relative is
yeah,
big.
yeah, the, yeah.
I see. And
So if
we
you,
using
yeah,
the same doping.
yeah, yeah. Normally for p-type doping for nitride, we use magnesium. While for N-type, we use silicon.
I see. So there are no other material to dope the P dope?
We can use carbon, but the
But the,
carbon is coming from group 4, if I'm not mistaken. And then the problem is carbon tend to what you call it, contribute to N-type or P-type. It's not stable.
I see. Okay,
So
understand.
yeah.
Understand.
So
Understand.
normally we use magnesium. Magnesium definitely we can get P-type.
Great. Very enlightening. So thank you
Right.
very much. Any more final call from question from the floor or anybody? So I think ada ke? Okay, tak ada. So I think I would like to thank you very much to Dr. Norzaini from IIUM for having the webinar with us today. It's very enlightening. Now we learn something about UVC, why and what's the importance of UVC, and also the challenges. So so brothers and sisters, students, ladies and gentlemen, there's always a challenge when you want to do research, and that's why there's always research, right? When you have challenge, you have research. And the point that Dr. Zainal is mentioning today on the dislocation, how your work, how to improve to reduce actually the number of dislocation inside the aluminum nitride on sapphire. Okay, thank you very much, and also thank you to IEEE Photonic Society in collaboration with us. Hopefully, please visit our Facebook and website. You can also visit the Facebook and website of INO if you have any more further question in the future or for collaboration. Before we end, can we take a photo for everybody? If possible, everybody, can you turn on your video? Then we can take a group photo. So now it's this online thing, so we take photo like this lah. Can everybody turn on their video for us to take a group photo?
Someone, let's turn on just for a while and then
Just for a while before we end.
come on, brothers, sisters.
Brothers and sisters, are you listening?
All right, thank you, Dr.
Okay, thank you, Dr. Bilal. Okay. So the students here, Dr. Noridayu.
Ah, okay, Anati, thank you.
Okay.
Where's the rest? Come on, Farah. Okay.
Baru saya tahu Anati ni muka dia macam mana.
Oh yes.
See, you have the camera, right? Then
We need to make a, what do you call it, another Zoom meeting between just us because we have many questions.
Yeah. So Anati, just feel free to let me know if you need help.
Okay, we
thank
are
you so
still
much,
waiting
Dr.
for the rest to turn on your video.
okay, thank you, Farah, Haja.
Ina boleh take the capture screen, boleh?
The green screen, yes, but should we wait for all?
Yes, we will wait for more. Oh, Dr. Huda Adiba also here. None.
Prof Mashkuri.
So anybody not from IIUM, can you introduce yourself? You're not from IIUM, just to get to know.
Fazmi, you're from?
Not from Kulliyyah of Engineering. Anybody not from Kulliyyah of Engineering here?
Dr. Fazmi.
Dr. Fazmi from where?
Dr. Fazmi. Okay, it's okay, Nadia. Okay.
There's a background music, Ina.
My bad, thanks.
So, okay, student from IIM, okay. Azmi, so, okay, Shannon, can you turn on for a while? Macam ramai segan nak turn on ke apa ni? Macam mana kita nak ambil gambar ni? How to make them into one space yang ada ni? Cannot. So, I think it's okay lah. Because the rest, many maybe have some students also have like a camera problem, cannot turn on the camera. You know, nowadays when we heavily use the laptop and everything, semua jam. Okay, Ina, you will capture your print screen
Okay, say hi. Assalamualaikum.
Kejap, alamak, silap. I will try. So maybe you can count now 1, 2, 3 so that we look okay lah.
Okay, 1, 2, 3. Okay, done.
For the next, we need to do that for the next next apa nama tu? Screen, Ina.
Next screen means?
Dia ada 2 screen. Dia ada 2 page. Okay, can do another one? Kalau Ina tak nampak. Okay, 1, 2, 3.
Alright.
Okay. Okay, that's enough. So thank you very much, everybody. And again, thank you, Dr. Norzaini, and we welcome you anytime to come to IIUM. So you can also do more collaboration and visit our labs. Let's end today's session with Tasbih Kifarah and Surat Al-Aus. Subhanakallahumma bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillahirrahmanirrahim. Wal 'asr innal insana lafi khusr إلا الذين آمنوا وعملوا الصالحات وتواصوا بالحق وتواصوا بالصبر. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Terima kasih menjemput.
Terima kasih.
Okay.